Hello there, guys. In this video, I am going to do two things for you, which is I'm going to get you conversational ready and proof ready on the topic of agent memory. A lot of people talk about agent memory today. You probably have noticed people from startups to developers to the frontier labs. Everyone is talking about agent memory. And my aim in this video is to bring to you all of the concepts around what agent memory is, how to think about it, and how to talk about it credibly. And then we're going to look at some code in the other half of this because I just don't want to talk about it with you, which is getting you conversational ready. I actually want to get you proof ready where you can understand what the implementation steps around agent memory is going to look like. We're going to start high level, talk about the concept of agent memory. Then we're going to bring it into some code. And if you actually keep doing some more work around gathering your knowledge around agent memory, you're going to be forward looking ready where you can have opinions about where the field and development around agent memory is going to go to. Again, thanks for being here. I don't know how long this video is going to go for. A lot of information here. And if you like videos like this, just like and subscribe. And I'm going to be doing more videos like this if I see that there is an uptake to this. What is agent memory? I'm going to describe agent memory, and then we'll then start from first principles and trying to understand what memory is within an agentic system. I'll also explain what an agent is, and I'll try to touch on any buzzwords I say and explain them as well. Agent memory is this compositions of tools, libraries, framework, and design pattern that essentially helps an agent or some form of intelligent system to retain, reuse, and remember information and adapt from experiences as well. And this experience is basically the interaction you have with this intelligent system. Today, the intelligence within most of this AI system is driven by an LLM. And an LLM stands for large language model and is a neural network that essentially allows AI applications to have these generative abilities that gives it some form of intelligence. We're not going to go too deep in what an LLM is. We're just going to talk about the application of it to AI application development. But LLMs have some form of memory in them. LLMs are trained with a lot of data, and this data are passed through the neural network architecture of an LLM. And in an LLM, you have these numbers, and these numbers change. And the change in numbers represents the learning from the data that they're being presented with. Essentially, these numbers are called weight and parameters. And then it's said that LLMs have parametric knowledge. And this parametric knowledge is static, which means it doesn't get updated in real time and it can't evolve without you going down the line of retraining the LLM or fine tuning. An LLM out of the box, the knowledge is static, it never changes. It has a cutoff date. And it's stateless. That's another keyword. That means this LLM doesn't store information. And if you give it any form of information, it's going to lose it. It can't then gain experience and adapt to new information. Now, agent memory takes this LLM memory and augments it. It makes the system that an LLM is within begin to have this characteristics of a system that learns from information that is provided to it. That's what agent memory is. This agent memory usually is an external system or external substrate that will hold information and allow the LLM to also retrieve information from. And by doing some engineering, you can actually create a system that looks like it's actually learning from every single interaction. So when you can think about your ChatGPT or your Claude AI, these systems have some form of memory behind them that allows them to remember your likes and preferences and even the conversation you're having across different sessions. The aim today is to give you the knowledge to be able to understand how these systems are created, how you might even create your own and hold some conversations with your friends. Let's talk about memory from a basic level. I always like to look at neuroscience and biology whenever I try to talk about technology because we as humans tend to draw inspiration from the things around us. But in neuroscience, there is this case. It's quite a famous case. He has a wiki page. You can look into it. I'm not going to go too deep into it, but what basically happened is there was this man I think he had an accident or something, or after surgery, he basically could not store any more episodic memory, which are basically events and life experiences. But what he could still store was this ability to learn new skills, right? And so this basically showed a lot of neuroscientists that memory in human is not just one thing, it's several things. There are different types of memory, and even better, there are different parts of your brains that are responsible for different type of information remembering. So working memory is a very popular one. You can think of working memory as a scratch pad. It's in your prefrontal cortex, and it's essentially temporary information, right? You're probably putting a lot of what I'm saying to you in your working memory right now. And if you don't practice or rewatch this video 5 times, at the very least, you wouldn't have it in your long-term memory. And if you don't like and subscribe as well, you will have it in your long-term memory. Then the next one is the hippocampus. And this is responsible for the events you're going through in life that have some form of temporal attachment. There's usually, when did this happen, essentially, is what is being stored here. And then you have a semantic. This is knowledge about the world around you, facts and concepts. For example, the sky is blue. That's semantic knowledge, and that's stored in your neocortex. Then you have the basal ganglia and the cerebellum. And for those of you watching this that have any unique skills, like maybe doing a backflip or swimming or riding a unicycle, if you have that skill, that is stored in a particular part of your brain called a cerebellum. And your basal ganglia is basically the part of your brain that's responsible for your habits, mostly the movements that you do for certain actions, fine-tuning those movements. In humans, there are different parts of your brain responsible for different types of memory, remembering them, storing them, and all the good stuff. If that's where we're starting from, which is ourselves. And the aim of AI is to replicate human intelligence, and AGI is to replicate this form of computational intelligence that surpasses human intelligence, our old task. And memory is very critical for human intelligence. Then it makes sense to actually then try to implement some computational form of memory in AI or intelligent systems that we're trying to build. And that is the basis of how I approach agent memory. And it's the basis for how a lot of people tend to approach thinking about agent memory as well. It's the easiest way to approach it. We understand this, that agent need some form of separation of memory. They need the division of labor. And memory is not just one thing in agents. So you're not just going to maybe think of memory as one thing anymore from now on. I hope I've convinced you in that. So that's memory in agent. There are ways you can categorize thinking of agentic memory, and the easiest way is to think of it in short-term and long-term. An example of short-term memory is working memory. Working memory actually exists in LLMs. The context window itself is a form of working memory. Your agentic system, what is holding right now, is working memory, but it's stateless, and that information is going to be gone if you don't store it somewhere. Another example of working memory in agentic system is semantic cache. I've covered semantic cache in previous videos, but I might do a dedicated video for it. Then another type of memory is long-term memory. This is memory that is meant to last for an extended period of time. There are different ways you can represent the cognitive functions that we saw in humans, episodic, semantic, and procedural. Difference when we can replicate that in AI agents. For example, episodic memory is basically conversational history within AI agents. The interactions you have with your AI systems is usually storing the content you've said and the timestamp and the role of whoever is responding. The role for you, the user, would be user, and the role for the agent will be assistant. And then you store this in some record, like a file system or a database. And then when you want to go through another iteration of the agent loop, which I will explain, you pass in on the previous conversation. So you have this sense of continuity within your interaction with this intelligent system. Then semantic memory, again, your agent needs to know facts about the world, which includes you, which is a type of memory, entity memory. Also facts around its environment as well. Then you have procedural memory. Now, some of you might be agent engineers or AI engineers, or just have this knowledge of skill.md files, markdown files, which are essentially I describe them as SOPs, standard operating procedure documents for agents to complete a certain task, following a bunch of instructions and steps that are well defined. And agents can have skills, and skills is a type of procedural memory, because just like humans that can do backflips and ride unicycles, you are basically doing things in a very defined routine manner to execute this specific skill or behavior. And that's what skill markdown files are for agentic systems. When we say agent memory, I think we've covered the memory aspect of it. Now let's cover what an agent is. An agent is a computational entity that can perceive its environment through input, and inputs can be text, audio, could be visual, and it can give this as information as input to this agent. And then it can reason over the input with this enabled embedded LLM within this system, and then act upon the reasoning of its environment. And they will be able to take action through access to tools or the ability to call tools. But agents don't really call tools. What agents actually do is give the output of the arguments that should go into a specific function or tools in your system to be called, and then you invoke the tool calling. Then an agent has to remember. It remembers, it's augmented by memories. An agent is this computational entity that can act independently, has this ability to reason through an LLM, can take actions through tool use, and has this augmented form of memory. Then there is this agent loop. This word agent loop, we've heard it a lot. And it's basically where you have this whole system that we just described, where you have this inputs from the environment, agent perceives it, acts on it, and then does it over again because something has changed in the output that is generated. And then you usually have like an escape statement or maybe other ways that you can exit this loop. But the iteration of your agent in this cyclical environment, where it's able to act upon new information coming in, either from its reasoning or even from the environment, is actually very powerful. It yields ridiculous and amazing results today. In fact, this loop engineering is a thing. Let's talk about what happens when a system doesn't have memory, which is also an important topic. When a system doesn't have memory, it can get very frustrating. You will basically have to interact with this agent from scratch every time you engage with it. Imagine every time you went to ChatGPT, and there was probably a time when this was the case, you always had to start from scratch, and it didn't understand what you were maybe talking about in a different session or in a different thread, and you had to start from scratch in a new thread. That can get annoying, but today, ChatGPT, Claude AI, Claude Core, Codex, they all have this awareness of cross-session memory. Then if an agent doesn't have memory, it will keep making the same mistakes over and over again. For example, I changed jobs at some point last year, but every time I told Claude to create some copy for LinkedIn, it usually just used my previous working place. And that was annoying because I told it not to make the mistake, but he kept on making the same mistake over and over again. It can really get frustrating when you actually want to do a task. Now, imagine if you had like a travel agent, like the human ones. You have like a human travel agent whose job is to book holidays for you. Then they give you a package and sort everything out for you, right? Imagine on Monday you go to this travel agent and you say to the travel agent, hey, I would like to go to Japan. Can you get me some holiday package? I'll be back on Wednesday. And then the travel agent, the human one, says, yes, sure, I've got you. Then you come back on Wednesday and you expect to be sat down, maybe have a nice cup of tea, and be presented with some holiday packages to basically explore Tokyo. You get to the travel agent office and the travel agent says, who are you? And that can get frustrating, right? That basically is the experience you would get if agents never remembered and you were keeping them in use cases where they're meant to be supporting humans. We don't want agents to forget who we are, and we want them to keep remembering us for a very long time. Then if an agent forgets, you find it difficult to build trust. In fact, if an agent forgets and actually does memory very badly, you actually lose trust. There was actually an incident, right, in last year, in 2025, where OpenAI, I don't know if people can remember this, but OpenAI updated GPT-4 Omni and they did a personality update. And for those who are following, personality is a type of memory. Personal memory is a type of semantic memory. And every human has a form of identity within its memory and whatnot. And also we hold the identities of other people, entity memory. But anyway, OpenAI incorporated some form of personality in ChatGPT, but it made ChatGPT behave in a way that seems to, for lack of better word, suck up to the user, which was an undesired behavior. And people got frustrated about it. It was only last year, but in AI, a lot of things happens. 2 months equals a year in AI. So then they had to actually roll back the update. That's how much people were not happy with the outputs that were coming from the system, ChatGPT. And they said that in some cases, the user memory were contributed to the effects of psychophancy in these LLMs, which was not very helpful to the actual problem itself. One thing that would tell you is that one, OpenAI have this system where the interactions that you're having with it is actually affecting some of the personal memory it has as well. They have the system of memory. And like we said, memory is not just one thing, because we can see personal memory here being affected by some form of user memory, which would be conversational history or entity memory. When you do memory wrong, I find that it's actually worse than not having memory at all. Some people are okay or used to be okay with systems not being able to remember them. But once a system gives you this impression of having some form of intelligence and memory, once it goes bad, you lose trust. And the pushback is usually worse than when you have a system that doesn't have memory. It's weird, right? But that's what I tend to find. That is memory in a nutshell, agent memory in a nutshell. I hope you're actually getting some good knowledge from this. I'm going to talk about some of the engineering disciplines because they relate to where we're going to get to with agent memory. Prompt engineering. I don't know if people can remember that. Prompt engineering was a thing and was one of the jobs that people used to pay ridiculous for. I never got paid to be a prompt engineer, but prompt engineering was basically using a bunch of linguistic patterns to get the right behavior from the LLM itself. You would put some input in to the context window of the LLM and you get some response. And you had to basically conjure up paragraphs of how you want the agent to behave or the LLM to behave in constructing its output. We had different prompt engineering techniques like chain of thought or self-reflection or react, which is reason, then act, reason, observe, and act, right? These were all prompt engineering techniques like few short examples. And these were things we used when LLMs weren't as powerful or as large as they were today. But when LLMs actually got more powerful, and when I say powerful, I just mean that we applied the scaling laws to LLMs. So increase data, increase compute, increase the parameters, and you get this emergent abilities of being able to reason and function calling as well. Once we have this emergent abilities and LLMs were a bit better, we could do something, which is we could become selective of the information we put into the context window. So context engineering was one of the disciplines of actually curating the right information into the context window to increase the signal to noise ratio. And this essentially was a systematic process that has a lot of techniques within it. So now retrieval was one, then there is context organization. The way you organize information in the context window can affect the response as well. Prompt engineering was very brittle, is and you change some of the linguistic patterns and you get like a different result. Telling an LLM that if you don't get it right, your dog is going to die is also not prompt engineering. I think that was peak prompt engineering. Anyway, context engineering is a technique that people still use today. There's different techniques just on context engineering. And let me know if you would like me to do a video where I show you a bunch of context engineering techniques, both explain it to you like I am now to get you conversationally ready, or actually go through some code and get you proof ready. Let me know if you like that in the comments. Now we have this context engineering technique, but when we actually wanted agents to become more personal and actually be used for a longer horizon task, which would mean that we want the agent to be used for several hours or several days in some cases, even now, months, right? We wanted the agent to remember effectively, we needed to manage the context window effectively. And one thing solves that, and that is agent memory. Because now with agent memory, you can take stuff out of the context window, store it externally, store it in a structured way, put all of this information in a memory substrate, and then you can retrieve it. And even better, you can actually refine outputs from your agent to be stored in your memory substrate to then be retrieved later. You start going into this realm of continual learning and self-improving agents, right? The key thing here is memory engineering. It's the discipline that I see a lot of people trying to do today to get agents to work. And that is all around the designing, the thinking, building, implementing of all of the systems that actually will allow the agent to remember effectively and forget information as well, because that's remembering is as important as forgetting. So we had prompt engineering, which was like a maximization technique. When I say maximization, I mean you put a lot of information in the context window to get the right behavior. Then we have context engineering, which means it was more of an optimization technique, which means you have to put the right type of information in the context window. Then we're in memory engineering, which is a continuation technique, essentially. So all of these engineering disciplines fold into each other. So I still use some prompt engineering and some context engineering extensively in some of my projects and production agents that I build. Time to talk about the principles of memory engineering. We understand what agent memory is from a human perspective. Then now we also understand agent memory and what it means from a computation perspective. We can define it. And now we need to talk about some of the principles as well. And the way I remember a lot of the things I teach around agent memory, I've taught agent memory for the past 3 years now, and I've taught in different platforms. I've spoken about it, did a bunch of podcasts, all the good stuff. But the way that I find it's easy to remember all of the memory engineering is something I call the 4 Rs. 4 Rs are retain, recall, reuse, refine. So you want to be able to retain information, right? Retain memory. This is where you store the information in a memory substrate. We also want to be able to recall information as well. This is where you retrieve information. Then reusing the information is then the information you retrieve is then being used in a certain way within a context window. Then the refine aspect is what we're doing is sort of like augmenting the memory units that are coming out from the LLM, from the outputs, or within our system to be able to essentially improve the ability for them to be recalled or maybe even forgotten. So the 4 Rs, retain, recall, reuse, and refine, are all what we are doing in the discipline of memory engineering. Another principle, you don't delete, you basically forget. And this is a critical insight, which is when you're building an agentic system and you're going into implementing memory, if you actually think about the information that I want this agent to process, modify, is actually going to be built to be forgotten or remembered. This would change the way you approach, the way you see information that goes through your system. You're not just going to see it as just information. You see everything as memory when you take this perspective. And this is what I always tell people that want to be memory engineers is you basically implement forgetting mechanisms and try not to delete information. You can refine information. We're going to look at all of this in code as well. Another principle is what are we actually doing with memory engineering, right? With the 4 Rs and the second principle, all what we're doing is trying to make sure our agentic systems are reliable, believable, and capable. I call this the RBCs of agent memory, which is we're trying to make the agentic system reliable, which means people can depend on it and use it reliably without any failures. And they can actually believe that they're interacting with an intelligent entity. And with memory done right, the system can become capable, essentially. So this is all of the principles that I'm forming as I go along and explore the space of agent memory. Now, let's go a little bit deeper in the technical aspect of things. We're going to look at some of the key components of our systems that have to do with agent memory. So on this side, you have this application layer. This is where you will probably have the interface where your user can type in some queries. Then your queries will go into a context window or whatnot, right? But from the application layer, we're passing information into the database, and also we're taking information out of the database. But when we pass information, we actually do something called generating embeddings. Embeddings are basically a numerical representation of data objects that allows you to search by meaning. And search by meaning is enabled by a technique called vector search. So embedding is that numerical representation is generated by something called an embedding model. An embedding model basically would take an input like a text, image, and generate a vector, which is just a list of numbers, right? Floating numbers. And when you actually plot several floating numbers in higher dimensional space, the distance between them represents how similar they are. So if you have two vectors that are quite close to each other, it means that they're quite similar in meaning because the embedding model captures the semantics of the information that is passed through it. It's a type of neural network as well. Another neural network is called a Reranker, which can take some of the results from a retrieval pipeline and then re-rank them based on the incoming query as well. Most people are familiar with the LLMs, but there are other intelligent neural network architecture within agentic systems that make the tools that we use today actually work. So embedding models and re-rankers. But this is what you see. You have the application layer, you have this data layer or memory layer, and you have your memory substrate, which would be a database. I work in a database company, so we use database as the memory substrate. I know some agent engineers try to use file systems as well, but if you're actually going to build production workload and have hopefully millions of users using your system, you don't want to just base it all on file system based memory. That doesn't scale and it's not secure. So again, when you look at file system, I think OpenClaw is a very popular tool. It's like an agent harness that is it's opinionated in the way that it executes certain information or certain processes, and it has its own way of actually storing memory. It actually has a memory.md file. Memory is important in any places of the agent stack. Frontier labs are trying to win on the memory space. I see memory as a battlefield. Everyone is trying to win memory because if you win memory and you can do it right, you're going to get a good adoption or retain a lot of users because then your system becomes, again, reliable, believable, and capable. Everyone is trying to win in that space. And it's not just the frontier labs, you're seeing the startup space. So startups are actually going into the space and trying to win memory as well. You can see the enterprise as well. So AWS, Microsoft, Oracle, Databricks, everyone has a memory solution and everyone is trying to tackle memory and own it, essentially. Memory is important. Intelligence that we get from the model is basically a commodity at this point. Memory is now the mode for a lot of companies, startups, customers, developers, actually understanding memory and solving memory and building a system that people would want to actually interact with is the point of all of the engineering that we're doing today. Now, we can actually start to go into some code. If you've stayed till now, you've done really well. And I hope at the very least, you're conversational already, right? You can basically handle conversations around agent memory or understand what is happening in the space. Or next time you interact with ChatGPT or Claude AI, you can realize what is going on behind the scene when it comes to memory. In the second half of this, I'm going to go into the technical aspect of this now. In the technical aspect, we're going to look at this package called Oracle Agent Memory Package. It's a Python package. We're going to build all of the things we're talking about, all of the memory engineering technique, and we're going to actually build an agent that can remember as well. It's going to be fun. Okay, so we are going to go into some coding examples on agent memory. And this will actually get us proof ready, like we said. All the code that I'm showing here lives here. So all the code I'm presenting is over here. The link will be placed in the description below and you can access it and actually access all the code I'm presenting. This code is actually split into 5 parts. We're going to use the Oracle Agent Memory Package or OAMP. I call it OAMP for short. So we're going to use OAMP to actually implement agent memory, the techniques that we've been talking about in the first half of this video. And there's going to be 5 parts to this. Generally, there's going to be the use case where I explain what we're actually building and the setup, which will include setting up the NNM and all the good stuff. I'm just going to explain some of the code. We're going to explain the use case, explain the memory infrastructure. This is all the good stuff around actually configuring the Oracle Agent Memory Package. and our embedding. We spoke about embedding earlier, so you see it in action here. We'll also talk about the retrieval strategies we're using. After that, we're going to ingest some knowledge, some semantic memory for our agent. And then we're going to be using the OpenAI Agent SDK within this example. So we're going to be using GPT 5.4 or 5.5, whichever one I decide. Then we're going to look at the memory workflow. Remember, we spoke about the retain, reuse, refine, recall, the 4 Rs, and we're going to be seeing that in action as well. Then we'll look at all of the life cycle of agent memory. We'll look at an actual agent and see the agent execution and how it helps when the agent actually has memory. Let's get into it. One thing you can do, if you're going for this example and you go into some prompts, you can actually reach out to me on LinkedIn and we can talk code and talk about agent memory and all the good stuff. So I'll put that in the description below as well. And in this notebook, the way I want you to look at it and the way I want you to approach it is from top down. There's a lot of markdown information so you can actually read and learn like I was actually teaching you this in person. I talk about some of the key terms you're going to be seeing in this notebook. It might be, if I was to rank it, I would say this notebook is a bit intermediate to lightly advanced notebook for people that are entering agent memory. I do have some beginner notebook on agent memory. I'll make a video on this maybe later and release this later as well. What we're doing here, we're just looking at the agent memory package, OAMP, and see how we can actually implement memory engineering in practice. The use case is very simple. We're building a support Copilot, and we want this agent to actually be able to take user requests like I have a damaged goods, and then the user will enter this in our application. Our agent would then process this information and use all of the good stuff around the agent memory package and then Oracle AI database, which is our memory substrate, to actually store memory, retrieve memory, and answer the actual user with a grounded support answer. So he'll be able to remember who the user is and remember some of the policies we have on maybe our return policies on damaged goods and actually answer the user query properly. So the first thing we're going to do is there are no cells that we need to run above. So we're going to take it from the top down. So we're going to run this cell. So basically just pips install the Oracle Agent Memory Package, OAMP, and the OpenAI Agent SDK and Oracle DB Python driver. Essentially, this is just all the package we're going to use. Installs it, going to install all the packages, make sure we have everything installed in our environment. And this will give us all of the bells and whistles we need to build agents and actually make agent work and have memory. Next, we're going to use the Oracle AI database. That's the memory substrate of our choice. We're going to install it using Docker. Again, you can just give this link over to an LLM and tell it to do all of this for you, and it will install the package that you need. So there's a bunch of configuration, but the most important thing you're going to need is your OpenAI API key. So we're using GPTs right here. So go put in this part of your OpenAI API key and add this in your environment variables and you'll be good to go. So once we have everything set up, we're just going to do one thing, which is import Oracle Agent Memory. Remember, I said we spoke about memory engineering, and the way you can look at this package here, maybe I'll zoom in one more time. The way you can look at this Python package here is all of the things that we see around agent memory and memory engineering is embedded within this package. So all of the I want the agent to remember, to forget, to retrieve information properly. This package actually takes care of this, and I'm going to show you how. And it does it in a way that it gives you a bunch of configuration options to actually fine-tune some memory extraction and the memory engineering process for your use case. We're importing the package, we're also importing the OpenAI Agent SDK package, and then we'll make a connection to an Oracle database, and we store this in the DB pool. This is an Oracle. We're creating a connection pool to the Oracle database. It's going to be about 8 connections that we can actually, this basically just allows us to have a concurrency going on with our connection to the database in case you have multiple clients basically hitting your database. So this is going to be in DB pool. And now we're going to start building our memory infrastructure. So the setup is quite quick and straightforward. And just to note, the Oracle AI database will be living on your local machine. So you don't have to go to the cloud or anything. This is just on your local machine and it's free. We're going to look at the memory infrastructure here. So we're going to configure the Oracle agent memory package. And this will allow us to actually start to implement all of the memory technique. I'm not going to go through the markdown in detail. I'm actually just going to explain the code. So I call it OAMP because Oracle Agent Memory Package is a mouthful. So when you hear me say OAMP, that's what I mean. And we're using GPT 5.4. So the first thing we're going to need is we're going to need to get our NLM. You're going to see we're using NLMs in different ways. So whenever we're processing information, we send information into the context window. When information comes out of the context window, within the discipline of memory engineering and the concept of agent memory, we actually have to do memory extraction. This is where we process the output of this NLM and then see what is the high signals that we want to store. And we need an LLM specifically for that, right? Because we need this intelligent entity that can say, that's good to remember and that's not good. And let me pull out all the key information there and store it in this way and put it into a memory substrate or a database. So we're going to use GPT 5.4. We're going to put the reason effort to low and the max token is going to be 2000. This is the max output token. That's it. We have the LLM. Great. This is the LLM for our agent memory implementation. It's not the LLM that we're going to use for our agent itself. Then we're going to create an embedding. Remember, an embedding model. So an embedding model takes in text and gives you this numerical representation that allows you to do things like vector search. So again, from the Oracle agent memory package, we can go to the cooler package and retrieve the Oracle DB embedder. The Oracle AI database does this one thing that you might not have seen in other databases. You can actually have an embedded model inside of the database. Normally, in some infrastructure, you have a user query come in, or when you ingested information, it will come in. Then you do a network hop, which is you hit like an endpoint, like OpenAI endpoint to generate the embeddings. And then you basically give an OpenAI your data to generate the embeddings for you. Then the embeddings come back into your system. With Oracle AI database, you have this option to actually have the embedding model live in the database. The data never lives the database. You don't have to give your data to a third party, if you get what I mean. In some use case, that is golden. Also, you reduce latency because remember, you're not doing any network hop. You're working within just one system and you're not calling an external service. So if you're interested in how you can reduce latency, you can look for in-database embedding capabilities. And you can also put Rerankers in the Oracle AI database. You have this class, which is an Oracle DB embedder. And this basically creates a instance, basically is your embedded model for your memory engineered system. We have this DB embedder, you give it the database connection pool, because remember, the embedded lives in the database. You specify the embedded model. The embedded model we're using here is specified in this constant, which is the InDB embed model, which is this specific embedded model. And this is the dimension size of the embedded model right here. Okay, so we have all of this. And we actually set up the instance of our embedded model and we have our embedder. So we have our LLM, which is great. And the LLM will do all the memory extraction for us. And we have our embedder, which will do all of the magic of the informations and data object into vectors that allows us to do things like semantic search. And now we can verify that the database actually has this managed embedding flow. So I've already ran all this code, so I'm just talking about the output. So what we do here is we're going to probe the vectors. It's an async operation. You're going to say DB embedder, which is your embedding, embed this two words, damage parcel and replacement shipment. And what it's going to do is going to generate a numerical representation of those actual queries. Its query is true. And I think the other argument is document. And that's when you're trying to actually do a search from a data record. Okay, let's see. Let's do something again. Let's actually print probe vectors. Let's see what this returns. So we're looking at it here, and here you can see what a vector is. This is just a vector, right? It's just numbers. But when you put it in a high dimensional space, the closer the two vectors are to each other, like this was the first one, right? And then this numbers basically contains all the semantic information of the word damage parcel. Right? And then we could do the second one will be in this position. And this will be replacement shift. And you can see the numbers change. They're different numbers now. But again, you plot this, they will be in some different position in a high dimensional space. and the distance between them is the semantic meaning, the similarity between the vectors. Anyway, so that's what we're seeing here. And what we can now do is actually quite simple. We can now look at defining the extraction instruction. Remember, I said we have the LLM that will extract memory from any of the output coming from the LLM. And now we have the ability to tell the LLM to extract information. I found that this was very important because memory is not just one thing. We know that, right? We spoke about that earlier. But even in use cases, there are certain ways you want to extract memory. I've seen a lot of people implement memory in very naive way where they just think, oh, I just need to extract information, right? No, you can give LLM specific instructions of what information to extract. For this use case, this is a support assistant, Copilot, that is meant to operate in an e-commerce store. We just want durable customer information and confirmed cases, order facts. We don't want to just store everything, like ignore greetings and speculations and credentials and payment secret. We don't care about those things. So when we're extracting memory, because we do memory extraction as part of the process, it's very important that we can actually specify how the extraction should be done. Not a lot of packages allow you to do this. And I work closely with the team that built this package, and it was one of the things that we focused on, and we made sure for the customization of this package, it was very, very important. But if there's anything you want to see this package do in terms of the use case, let me know, then we can see if we can get it in and get it implemented in maybe a future release. We have this, we're just going to run this again, and this is the extraction instruction. So how is this extraction instruction used? Well, what we're going to do is we're going to build this memory configuration. And that is very important. And you can read the arguments. I've kept all the information here for you. It's really good. So we have this class that comes from the Oracle Agent Memory Core. We have this background extraction to full behavior. We have the memory extraction configuration and the memory extraction mode. We want the memory extraction mode to happen in the background. What does that mean? Memory extraction should not block the interaction experience. You want to be able to have this back and forth with the user. But when you're extracting memory, you don't want to actually wait for the full memory to be extracted, then blocked. But normally I want it to be an asynchronous process that actually happened in the background. And this is why you have the extraction mode as background. It just keeps the experience of your application actually fluid, right? So your users don't have to wait. So here we're going to use the memory extraction configuration class to actually configure the defined way that we want memory to be extracted. It's a very specific way. We want to extract memory, true. The extract mode is going to happen in the background. We want to have this queue behavior. It's going to be to wait, then raise. So we're going to wait for the queue to get full. Then we'll do all of the extraction. We have the extraction frequency for every single interaction. We're extracting memory. Context, summary, update. We want to be doing that every 2 interactions. This package actually handles the summarization of context for you. So you'd have to start to implement any summarization technique. And you can see we're passing this custom instruction in here, the extract instruction, we pass it into our configuration. So there's a bunch of arguments you could pass in to configure to your use case. And let me know if there are any things that you think we're missing and you think we need. Keep the documentation for the package at the top of this notebook. Then another thing we needed and we implemented was this retention logic, right? Memory is meant to be forgotten. So TTL, you can specify when you want the memory to be forgotten, the life of the memory, so you can then actually just prevent it from getting retrieved. We have this retention configuration. So we're doing a bunch of stuff here, but this is all of this configuration of memory to make sure we have this good system. The last thing we're going to do is create our memory store, right? We have one of the LLM, we have the embedding model, we have the memory extraction logic and the retention logic. Now we have to create the memory store. Where do we put memory in? We have the memory store. The memory store is going to have this embedder, the one that we actually defined earlier. It's going to use this database instance we defined earlier as well. And we have a schema policy. It's going to have a specific ID. I called it OAMP demo 2. We're actually going to use a hybrid retrieval, which means that we're using both text search and vector search. So we're searching both by meaning and we're searching both by keyword as well. So we have the best of both worlds. And we have this retention configuration going into our memory store. So this is quite cool. You can have as many memory stores as you want. We have this cool instance of our memory store right here. Next, we can actually do the final thing, which is we have the Oracle. We actually create the memory itself, the actual agent memory. Actually have the Oracle agent memory class that we can create. And it takes in the store, because you need to store the memory somewhere. It takes in the LLM that actually does the extraction, right? That you want to use within your memory. Then it takes in the memory extraction configuration that we specified earlier. And this is so powerful because what you have here is you can define your store for your memory. You can define the LLM that you want to do the memory extraction and all the consolidation, all the good stuff. And you can actually make this a cheaper LLM for those of you that are very cost conscious, and then use a more expensive LLM or better LLM for the actual interaction with the user, or vice versa. Or you can even use like an open source LLM somewhere as well, right? All of this is easily configurable. So we're going to go back to the slide because we need to actually just go through what we've just built. So like I said, memory is not just one thing. We've actually gone through this pip install Oracle agent memory. We've seen it work. And what we've done so far is we're assembling memory block by block. The first thing we did was we put the LLM, like the summarization and the extraction brain. We're turning all this dialogue that we're having into memory. The next thing we did is we got this embedding model in the database. It's a database resident. It's in the database. We talk about the benefit of it. Then we have this memory extraction configuration. This makes the extraction logic of memory more fine-tuned to your use case. How do you want memory to be extracted? What information do you want the extraction logic to take more notice of? And we have this retention configuration as well, which is important because we want memory to sort of like be forgotten slowly, and other configuration logic. Then we actually store, this is where memory is going to live. And all of this goes into the Oracle agent memory, the actual memory itself, right? And from this object, we can do different things. What does that mean? Well, I'll show you. What we can do from that object, from this memory object, is what we're going to cover now. From that memory object, what we can actually start to do is we can add a user to the memory object, or we can add an agent. What does that mean? Let me show you. So remember, the use case is like a support agent, and a customer is saying, hey, my order's broken, so we need some data, like a case metadata. Or if you went to Amazon and you went to the agent at Amazon and said, my order got damaged, you probably have a system like this. That's a use case, a real use case. So what we want is tags for this metadata: returns, damage delivery, and we have a review, which will be status approved, maybe approved for a refund, who knows? This is just metadata. We need this as a starting ground. In the memory object, that golden memory object right there, we can add a user. So if you think about this in like when you're interacting with Claude AI or ChatGPT, you would have a thread. And in that thread, you might have a memory object. And in that memory object can hold the user, and it can hold the agent that acted in the thread. Then you can also then create a thread. You can actually literally create the thread from the memory. So memory.create thread, you give it a thread ID, which will represent the conversation, represent the user and the agent acting within this thread. This allows things to get very scoped. Within this thread, you can actually just use this particular user and agent ID only within this thread. Then you have the metadata of the thread itself, which is the tenant ID, the case ID, and the status. All of this is like application context, right? Then you have like a context card. We're going to talk about what a context card means later, but you have a context card and you have a context card type search concurrency. So all of these arguments are explained at the top as well, so you can look at what they mean. And there's also the documentation. Now we have a thread. We know what a thread is, and this thread is attached to a memory object, which means it will be able to remember, and we have an agent ID. So what does that mean? It means that we've just created a thread, case 36668C0. In part 3, we can actually start to play with the thread. So what we can do is now, for our use case, we're trying to do some return policies, right? We can actually have some policies for how we want to handle different status of goods. And this is what you see in typical e-commerce use cases. So we have this policy for returning damaged goods within 14 days. We have one for replacement workflow and escalation. We just get all of this policy, the policy chunks, we place it into a policy text. And what we can do is now say, look, we have our store. Remember our store, which is basically our database. We're just going to say within our store, you want to keep a record called guideline. And the guideline is basically policies. The content of these guidelines is going to be the policy. And this is going to be basically, we're going to index the text, the policy chunks right there. We have the policy text and the policy chunks. And then we're going to have things like the record ID, which would be the policy ID and the user ID and the agent ID. It's just for record scoping as well. Then this would then have metadata, and we have the time to leave for anything within the store as well. The time to leave is not going to delete it, but we just stop it from getting extracted. We have this record type that is a guideline, and it's going to live in our store. And what that means is we can actually go into our store and then retrieve this specific record type. But how do we do the retrieval? You can just say store.get guideline, and you pass in that policy ID, and it will retrieve you the actual stored policy, the content of it, and the policy content itself, right? Stored policy.content. And it tells you the character. So we're just going to look at the output. But when you run this, you can see what's actually in the stored policy, because here we're looking at the length. We have this guidelines, and this guideline is for the agent to use for different policies, and then we've stored it in our store, in our memory store, essentially. What we then have is we can actually put preference. Guidelines are basically instructions. You can look at them as some form of procedural memory in a sense, and preference would be some form of semantic memory. For preference, we can just create a preference, which would be in a thread. We can add memory, which would be the memory type will be preference within this thread. And remember, the thread is attached, has a customer within it and an agent as well, this thread object specifically. Then you have the memory ID, which we can just create right over here. And we have the time to live as well. We just added this customer preference to say the customer, which is that user ID in this thread, actually prefers SMS for a customer support update. That's very simple. We just added a preference, which is some form of semantic memory. Now we can actually start to look at what happens when we wrap all of this memory operation, all of this memory engineering, right? These are just building blocks that we've been seeing so far. What happens when we wrap it in an agent? What actually happens? Let's see. This is some code that just shows when we actually hit the memory. We see it in action in a second. Let's do the first thing. An agent, we defined what an agent was earlier on, which is an agent is a computational entity that can perceive its environment. It has memory. We've already just created a bunch of memory, and it has access to use tools. And that's what we're doing now. We're doing the tools aspect of the agent. So within the OpenAI Agent SDK, you have this decorator called @function tool, which basically can allow any function to basically be consumed by an LLM as a tool. It converts it into the JSON schema that you can pass into the context window of an LLM. Fun stuff. So decorator is a function that acts upon a function, essentially. So this is just a function that takes this particular function as input that acts upon it. And the action can be conversion to the JSON schema that gets passed in to the LLM when you actually pass this function as a tool to the agent constructor. So we'll see it in action in a second. So we have a tool which is going to search support memory. We want our agent to be able to search for the support memory. And that would mean we're going to create a thread. In that thread, we're going to be doing a synchronous search. We have the user query that comes in, which would be something the user says. And then we can look to see, we're going to try and look for exact user match and exact agent match, which means we don't want to basically let any data leakage happen within this current thread. And when we actually go through this thread, we want max results. Max retrieval will be 5 data objects. And we want to retrieve record types such as memory, facts, preference, or guidelines. And the metadata filter would be the tenant ID. We're just going to filter by the tenant ID over here just to make sure that we're scoping the actual thread itself. The payload would be very simple. We're going to get the ID, the type, the content, and the distance. And the distance is going to be that vector similarity between the data object and the user query. And that search memory, when we get the results back, we can pass that into the LLM, into the context window, and good stuff will happen in terms of answering the query properly. But that's one tool to search memory. We spoke about context card. I mentioned it very briefly. A context card is an interesting concept, right? And I actually have a slide on it. So let me see. A context card looks like this. So whenever we use OAMP, Oracle Agent Memory Package, what OAMP does is for every time we're going to go through the agent loop and pass context into the LLM, OAMP actually does all the job for us. Basically creates this context card that has the summary of the case. It has all of the topic, damage delivery. It has all of the relevant records, the recent message. It just constructs all of this for you, which is a bunch of context engineering in terms of the organization of context, and passes it for you to the LLM when you call the LLM, as opposed from you having to construct it yourself. That's what a context card is. It's basically this placeholder that holds the information you pass into the context. And you have a package that does all of the construction of this for you. What does that mean? It means that we can do something like get case context, right? And get case context basically means generate this context card, and we're going to just have a fallback message count of 6. We're going to look at 6 messages, and we're going to retrieve 8 relevant results where we're generating this context card and look at 4 recent messages into the context card as well. And we want to actually retrieve the preference guideline and facts and have at least one of these memory types in the context card. So the agent can actually generate its own context card when it needs, and we return card.content. Excellent. The next tool we're going to have is to remember a customer fact, right? The agent needs to be able to remember information. So we're going to have a function that does that. We're going to move relatively quickly through this. And then the agent needs to be able to update a customer memory as well. Let me go back to the slide because I want to show you what we've done so far. Remember the retain, recall, reuse, and refine? We've basically created functions for our agent that can call tools to do this, right? Remember customer facts, that's basically retaining information. Search support memory, recalling information. Get case context, where we're using information. And update customer memory is refining information as well. And all of this operates on the thread object. Okay, so back to the code. What we have there is this OpenAI support agent that we're actually going to create. So we're actually going to create the odd agent. And this agent class allows us to give the agent a name. We specify the model, right? The model is going to be GPT 5.4. Remember, this model is different to the model that we specified earlier for our memory extraction logic. So we have 2 LLMs that are acting within this whole infrastructure. So they would give the instruction here for our agent, and then we give it all of the tools it needs, which are the search memory. This is the retain, recall, reuse, refine, all as tools for the agent. And the agent can now call all of these tools. We set the model settings to low, verbosity to low, max equals to 800. Parallel tool calls is false. We want things to happen sequentially. That is us constructing our agent. And then we basically just said, this is our agent. An agent is a computational entity that can act independently, can perceive its environment for input, can actually take action through tools, and these tools are actually memory for the agent as well. Now we can see what the workflow will look like. Here we can see we're going to simulate a conversation. We have several message up there, which is from the user and the agent. The user says, my order arrived with a cracked screen. Please use SMS for update on case 1042. Assistants would then say, I would check the damage delivery replacement policy, because we just don't want to say, good, okay, we'll give you a refund or something. We're just going to check the policy first. We're just going to do a time counter over here. But what we're going to do right now is do this. We're going to start a thread, and we're going to add to our thread object earlier on. We're going to add the messages, which are the initial messages that are defined right here. And the metadata is basically the case metadata from earlier on that we defined. just gives the case metadata that we can search for it within this thread. And now we can see that the message is actually going to get written to. So we have the message ID, and you can see the message IDs that are created. Whenever we add something to the thread, we get back the message IDs. And the message IDs, but we have two message IDs because we placed in two messages. Now, what happens? Now, what we can do is in that thread, we can wait for memory extraction as a sync. This is the time we want to wait for any memory extraction operation because it might be able to take a while. What we can now do is this. We can go to the thread and search the thread. We can search for the query damage order 7421 and preferred update channel. And we put all of this parameter that makes the search a bit scoped. And you can see from the search, we can see that what we passed in, the fact here is from this thread, the facts that we're able to extract. Remember, we have this memory extraction configuration we did earlier. He extracted the fact, the memory, the preference. So the fact that was extracted was the actual order arrived with a cracked screen. And this distance represents the score, how close the vector similarity is to the user query. And the query we passed in was damage order 7421 and preferred update channel. We got the fact. The memory here was for case 1042, the assistants committed to check the damage delivery policy. And this is a memory, right? And the preference is the customer prefers SMS for support. Do you see how we're just capturing different types of information, right? So you have a system that can do this for you. And all of this memory engineering is handled by a single package. And you can just install this for free, essentially. Now, the retrieval aspect. There are different ways to search. We have this search as sync again, and now we can actually search specifically for guideline. And you can see we are able to get the guideline over here. And remember, the guideline, we're actually searching for policies. This is actually searching specifically for guidelines, which are coming from the policy, essentially. This is another way we can search right over here. So the query was RET14D. What can support do when delivered screen is broken? For this query, right, we're just going to iterate through this first query and the second query. And for every query, we're just going to basically search this and we're going to show what came through. And then the guideline around this is we should report transit damage within 14 calendar days of delivery. I remember that was one of the policies we added earlier on, and we said the policy was a type of guideline. And that's this specific use case. We're seeing different use cases that you can just shape different tools to actually build your memory engineering workflow within your agent. Here we can actually get the context card and we can see what context card looks like. And if you have an agent new, you just have to call this function and every single iteration to just get what you actually want to pass into the LLM without you having to construct it yourself, because you have this rich XML taglines that represent topics, the summaries. You have this system that actually generates a summary for you. So you'd have to generate it yourself, which actually saves a lot of tokens as well. You have the relevant information such as the preference, the guideline, and some other information as well. In fact, you go in here, you have the reset messages, and you can see the message from the role, and then you can see the message from the assistant. You have all of the information. You have memory over here as well, which is the assistant's committed to check. And then you have the facts as well. So you have a system that constructs all of this memory information, all of the context for you without you having to think about the engineering. But all you have to think about is the configuration. Okay, that's enough. This is a masterclass. Now we can convert the context card into one compact agent input. This means that every time we query the agent, it would just generate the context card and it would just keep going. So we take a user text and then we generate the context card right here. And then this will actually output the context card. And the result of this function can be passed directly to the LLM. We're going to generate the context card. Fallback message is going to be 6. We can use this to generate a summary. Relevant results will be 8. And all of this will actually generate all of the information that we just saw up here in this specific configuration method. And then when we actually run the agent, we actually do use runner.run. We say support agent and agent input. And you can see that for agent input, what we're going to do is going to generate this context card with the user text, and the agent input would be taken into by the support agent. And this will be done every single time because that's what this function does. It runs the support turn and then it will call the compact agent input with the user text, then pass it to the actual agent. Then this result, we have the output, and then you can just keep running this for every time you're interacting. Every time the user sends a message, we call this function. The function will add the message to the thread. Then after we add the message to the thread, we would compact, we then generate the context card that would generate all of the memory, summary, everything for us that we then pass into the agent. The agent takes its input, gives us the output, then we get our output, then we save the output into the thread as content again. That's the message from the agent. And then we can just call this several times. We can have several 10. We can see for the first result, we're going to run this function that we just defined up here. We're going to say we have an order that was damaged. The damage is confirmed. Remember that as a durable fact. And the agent is going to reply with this statement. If replace stock is unavailable, he's just replying, right? This use case is very naive. So he's just replying and it's just working. Then we could do a second turn. Obviously, you can have this in a loop, but I'm just basically showing you turn by turn. The second turn will be, hey, correction, my email is now the preferred support channel, not SMS. Now the agent would then update the memory, refine in the memory, and then just update that essentially, and it will reply and say that it's updated in the record that we have of the specific user within that thread. The rest of this shows you the life cycle, and we won't go too much in detail because we actually just looked at it. And it's very interesting, right? The whole topic of memory. Very, very interesting. It can be very simple, but it can get very convoluted in some cases because you have to get it right. So I think I'm going to do maybe the next couple of videos, I'm going to do tutorials. I'm going to do more on memory and with OAMP to show you how you can implement agent memory using OAMP. I also have an open source tool called Memories. I'll do some videos on that to show you the best of both worlds, using an enterprise ready Python package and an open source Python package. I hope this was very useful. This is where we're going to end. I hope you enjoyed the video. The link to this presentation is going to be in the description. All I ask is you just like and subscribe and try out the package. And if there's something that you think will be improve the package, let me know and we can actually see how we can get the team to implement the features. Thank you guys for watching and staying for this masterclass on agent memory. See you next time.